Thank you very much. Can I get my first slide up, please? There we go. So, welcome to Java Today and Tomorrow. This talk is a bit about Java today, but it's also an attempt to peer into the future and see what's coming down the road. There'll be quite a few demos here. If you see me make a mistake, and I'll probably make at least one, feel free to shout out. Sometimes that's actually helpful. Live demos are still kind of a tricky thing. A few questions here and there are okay, but this isn't a Q&A, so choose your questions wisely if you have them, and I'll repeat them and try to answer them. If you have further questions, I'll be hanging out at the Oracle booth out on the show floor right after this session. Okay, before we look at specific features, let's first consider how it is that we decide what features to add to Java. We don't just add stuff because it's cool. We don't just add stuff because other languages have it and we're jealous and we have to keep up. We actually do it for a reason. We do it for two reasons. The two reasons that drive Java forward, that have driven Java forward for almost 24 years now, and those are two big goals. The first one is developer productivity. Java is about helping developers build and maintain large and reliable programs. It's not just about one-off scripts. It's not about building things that you're only going to use for a few days and then you don't worry about it. It's about building things for the long haul and being able to maintain them effectively. The other big goal is program performance. Program performance, of course, can be measured in many different ways. You can measure time. You can measure startup time and latency and throughput. You can measure space, whether it's static space or dynamic space at runtime. You can measure scalability from going from like little iPhones up to really big iron. For almost 24 years, we've pursued these goals in the face of constantly evolving factors, including new programming paradigms such as mixed functional and object-oriented programming or data-oriented programming, evolving application areas such as big data and machine learning, evolving deployment styles. Applets are effectively dead. The browsers killed them, right? And now we're deploying to clouds and app stores. And of course, evolving hardware, terabyte memories, deeper memory hierarchies, vector and SIMD instruction sets on GPUs, and deeper and ever more numerous processor pipelines. Let's take a look at how we're pursuing these two big goals in the light of all these factors and some of the major projects in the OpenJDK community. These are, for today anyway, Amber, a project to right-size language ceremony. This is being led by Brian Getz. Loom, bringing continuations and fibers to the Java virtual machine and the entire Java platform. This is being led by Ron Pressler. Panama, bringing a better foreign function and foreign data interface to Java. This is being led by Maurizio Tremadamore. And finally, Valhalla, value types and specialized generics, being co-led by John Rose and Brian Getz. Let's start with Amber. Amber, right-sizing language ceremony. Well, what does that mean? So I think we're all familiar with one of the big pain points of Java in that it requires a lot of ceremony. There's all this boilerplate, and this is especially painful in this modern era of data-oriented microservices, having to write verbose POJOs all the time. Oh, come on, can we please get past that? The solution as we see it is a series of pretty reasonably small language features delivered over time that over time will all knit together and let you express more clearly what you mean. We could just say, okay, we're going to attack the boilerplate problem and make Java as terse as possible and turn it into APL or something, but then it would be unreadable and unmaintainable. But instead, we're going to make it easier for you to express what you mean, and we think that will allow the boilerplate to take care of itself. Here's an example. Local variable type inference. Many people sort of naively and understandably think, oh, well, Java, yeah, it doesn't have type inference. Type inference is for those fancy languages like, Haskell and ML and all the researchy stuff like that. But in fact, Java has had type inference for quite a long time. We introduced some type inference in Java 5 when we when we introduced generics. So you want to make a list of strings. we could have designed generics like this. So you would have had to write collections dot string in pointy brackets empty list to get an empty list of strings. But of course, the compiler knows that this needs to be a list of strings because of the declaration on the left-hand side. So we just, you can just write collections.emptyList. As Venkat Subramanian likes to say, that you want the compiler to work for you, not you to work for the compiler. In Java 7, we introduced the diamond operator, which led to further boilerplate reduction. You want to make a new array list of strings. Well, you used to have to type new array list, pointy brackets, string. But you've got the declaration on the left-hand side. Again, the compiler knows this is going to be string. So as of Java 7, you could just type the empty diamond operator, and boom, the compiler fills it in, and you're done. So these were fairly small additions of type inference to the language. In Java 8, when we added lambda expressions, we used type inference on lambda parameter types. We could have required that every lambda, whenever you use a lambda, you have to declare the type of each and every parameter. But again, the compiler can figure out what that type needs to be. So while you can write it like this, and sometimes it's good to include the type information just for clarity in your code, you can also omit it and just write the plain S, or in parentheses, S comma T, whatever all your parameters are. So going further, in Java 10, we introduced local type inference. Here's a simple example. This is code you could have written in 1997 in Java 1.1. Buffered reader equals new buffered reader, new file reader, dot, 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 dot. We're all familiar with this. And it's just kind of, well, we know it's a buffered reader. From reading the right-hand side, the compiler knows that. You don't have to type buffered reader, really, on the left, on both sides of the assignment again. So local variable type inference allows you to type simply var. So this is for local variables only. You can't use var on fields. You can't use var on method parameters. And it's not dynamic typing. This does not mean we're turning Java into JavaScript. It's still fully statically, strongly typed. It just means less keyboard typing, and hopefully less work to read the code. This works out especially well in a sequence of assignment statements, as we often see. For example, trying to open a URL, and you get a URL connection. You want to hook a scanner up to it, and you've got these types on both types or similar names on both sides, and there's a lot of redundancy. If you can just use var, then the code is easier to read. It's also a little easier to write. One caution, though, you probably want to be a little more careful in choosing variable names. When you always have to type, you always have to put the type on the left-hand side. It's very tempting to use extremely short variable names. You might want to choose things that are a little longer, so that it's clearer further down in the code. So local variable type inference, we introduced that in Java 10. It's in some detail. It's described in JEP 286. If you're not familiar with JEPs, JEPs are JDK enhancement proposals. They're sort of the unit of significant work in the OpenJDK community, and they feed into JSRs and all of the standard stuff when necessary in order to make things official. But you can find JEP documents on the openjdk.java.net website, and they are a useful source of information. Okay, next, let's turn to another feature, raw string literals. How many people use regular expressions? How many people like regular expressions? Okay, yeah, so we all have two problems, yeah. so here's a really simple use of a fairly simple regular expression. You want to see if the stupid constant string matches this regex on the right-hand side, consisting of three characters, all of which are word constituents. And yeah, it's it's a little clunky because, well, you've got you need the backslash to introduce the W's that are telling the regular expression engine to match word constituent characters. But since you're in a double-quoted string, you have to type the backslash twice. And this gets even more fun when you have a regular expression that's trying to match backslashes, and you get to type the backslash 4 times. So that's just really tedious. With raw string literals, you can just type this. Now, the syntax is a little hard to read, so let me make that bigger. Backticks. we looked at the keyboard and said, oh, haven't used backticks yet. Let's try those. So you type a backtick and then some text and then another backtick. That's a raw string literal. There is no interpretation of backslashes or anything else except the next backtick. So you can type in there whatever you want. Actually, sorry, I lied. There is a little bit of interpretation. If you happen to have a new line in there and you're in Windows and it's carriage return new line, then we just collapse that into a new line because we had to do something and that was the most common thing. Anyway, so backticks introduce raw string literals. You can use this for a variety of problems, not just regular expressions. If you're on Windows, you've probably had to write code like this, where, well, path name, file system path names have backslashes in them. Why didn't they choose forward slashes? I don't know. So instead of that, you just use raw string literals, and it looks more like, kind of what you expect. You can also have multi-line string literals. So we've probably all written quick and dirty code like this. Yeah, you could go use some fancy XML API to do this properly and write a lot more code, but you're just trying to get something done. So you do it quickly, and you write in a string constant, but it's multiple lines. To make it readable, you use double quotes and string, string constant appends with pluses, and you get this sort of ugly stuff. You can have a multi-line raw string literal, and you just write this. So 3 backticks introduce a multi-line one, and 3 backticks terminate it. And you could have single or double backticks in the middle if you really want it. And again, as I said, carriage return line feeds on Windows are reduced to just line feeds in this case. To make multi-line raw string literals easier to work with, along with this feature will come some additions to the Java-lang string class, including, for example, a method called align. When you write this in your code, you want to indent it so that it looks nice. But of course, all the extra white space that's at the beginning of each line, you probably don't want that to be in the actual string literal. So the align method will go through all the lines, figure out what the least amount of white space, the largest common white space prefix of each line, and then remove that from each line, so that what you get in your program is actually what you expect. Okay, so raw string literals will be in Java 13, hopefully. We'll admit to experience here. We actually had raw string literals in 12, but we took them out because they weren't ready. In 12, they were a preview feature. In 13, they will be a preview feature. What is a preview feature? A preview feature is a feature that we think is almost nearly done, but not quite. So it's in the specification. We put it in a release so that we can get that last bit of feedback on it, but it's not enabled by default. If you want to use a preview feature, you have to type -- enable preview at both compile time and run time so that to make it work. We had this in as a preview feature in 12. We decided not too long ago that it wasn't as baked as we thought, so we pulled it out. We'll put it back in hopefully in 13 as a preview feature, and if that gets enough bake time, we'll make it final, a non-preview feature in 14, 15, whatever makes sense. All right. Let's move on to a whole different kind of example in Amber. Consider the canonical enum for days of the week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And suppose you want to compute the, for any particular instance, you would like to compute the length of its name. Well, no, we could cheat. You just get toString and take length on it. No, for the sake of this example, we're going to write a switch. So you've got an int num letters. You write a switch statement. Case Monday, Friday, Sunday. Num letters is 6. Tuesday at 7. Thursday, Saturday it's 8. Wednesday it's 9, and so forth. And just to be safe, we have a default case to throw an exception in case we forgot one. Now, all kinds of things can go wrong here, right? You could forget a break statement. You could forget to assign to the num letters variable in one of these cases. You could forget one of the cases and also forget the default, and stuff would just fall through, and num letters wouldn't be initialized, or it might have had some old value in it. As Brian Getz likes to say, this isn't the language helping you out. This is the language daring you to make a stupid mistake. What's going on here? Well, we're just computing an expression, so let's write it that way. And here's how you can write it in Java 12. Switch, that token can now introduce an expression. You switch on the value of some expression. You write your cases. We borrowed the arrow syntax from Lambda here. We use that to indicate what the value of the switch expression will be. And you don't need to use a default. You don't need to provide a default case. Since enums are final, the compiler, through some fairly simple analysis, can determine that you've covered all the cases, you don't need a default. And if you haven't covered all the cases and you don't provide a default, the compiler will tell you about it. So switch expressions are in Java 12. They are a preview feature, and hopefully they'll be a final feature in 13 or 14. So if you're curious, please try them out and let us know what you think. Okay, let's move on to some features that are not yet in any early access build. Consider the classic Pojo. We want to work with points. A point has an x position and a y position. It has an accessor for the x and an accessor for the y. Really simple, right? But actually, oops, I forgot a bunch of stuff, didn't I? Oh yeah, we need equals, we need hash code, we need toString. Okay, so yeah, we type all that stuff out, or we ask our IDEs to generate it for us, and they spit it out, and hopefully they get it right. IDEs can generate this stuff, but they don't help with reading it. And it's really easy to catch corners, and it's really easy to cut corners, and cutting corners leads to bugs, and bugs lead to hate. No, never mind. Another thing about this is we've got a class here, but one of the great things about classes is they encapsulate, but we don't actually need any encapsulation here, right? We're not trying to hide anything. There's no secret internal state. There's no magic internal methods here. It's this thing is just a transparent container for some data. Why can't we say just that? Well, with records, we can. You just say record, point, double x, double y, and you're done. All that Pojo code is replaced with just one line, because sometimes data is just data. So with records, there is a certain amount of customization that's possible. If you want to provide your own hashing algorithm, you can do that. You can override the default style of hash code method. You can customize constructor. You can add methods. You want to have the mathematical norm. You can do that. You can customize constructors to check preconditions on construction. What you can't do is add additional instance fields. So you can't add additional state, because that would violate the invariant that the record is just a transparent container for data. Records are immutable. It's a gentle nudge towards a more immutable style of programming in Java. If that doesn't work for you, you can always fall back. Write a class like you do today. So we have a prototype implementation of records. There is not in any early access build yet, but it probably will be soon. So that's been a quick tour of some select features in Amber. If you'd like to know more, you can stay in this very room, because Brian Getz at 11:10 a.m. this morning will talk about Java Futures 2018, the 2018 edition. All right, that's Amber. Any quick questions? Can you get what? Can you get a backtick in a raw string literal? Yes, you can. We're not quite sure what the best way is to go about that. In the version that we had for a while in 12, there was a very slick way to do that, but it turned out to be kind of confusing, so we're not going to do it that way. Okay, so let's move on to Loom, continuations and fibers. And now please bear with me, because I need to change from this laptop to that one, and hopefully this will all work. Okay, talk amongst yourselves. Okay, did it work? It worked, yay. All right, here we are. Loom, continuations, and fibers. Oh, sorry, I forgot one more device. How many devices can you use at once? There's a prize for the winner. All right. Note to Matthias, a bigger stand would be nice. Okay, somehow we'll stumble through this. All right, it's now demo time. Let me see if I can arrange all this stuff. Okay, we're not in California, there won't be an earthquake, it's fine. Okay, here I am. Let's get into the right directory. Here I have a very recent build of the Loom repository from OpenJDK. Built this just a few days ago. It's JDK 13 plus the very latest and greatest Loom stuff. So let's get into JShell here and take a look around. So Java has one of the cool tricks of Java at the very beginning was sort of sneaking threads into a popular programming platform. Threads have been a kind of specialized thing. Java became this mainstream language that had threads and made them popular. And threads are great, right? It's to many people a fairly natural way to express concurrent programs. We all know how to make a thread. We have RT new thread. Let's do this. System type here. Oh, this is so slick. JShell now does paren completion, by the way. Isn't that neat? It didn't used to before. It was awkward. OK, so here we've got a thread. We start the thread. And boom, it runs, it prints hello. OK, yeah, big deal. So threads have grown to become kind of big and heavyweight. There are lots of different methods on threads. Some things which, frankly, as is often the case, we look at some of the early Java APIs and we scratch our heads and think, why did they put that in there? Thread groups? What are those about? They're actually not really useful for anything at all. Threads have priorities that actually don't mean much on almost all platforms. Threads have a thing called context class loader, which turns out to have been a fairly awkward mistake. Every Java thread corresponds to an operating system thread. And in the cost model of operating systems 20 years ago, that made a lot of sense. But nowadays, threads in operating systems are kind of heavyweight too. They're expensive to create. It's expensive to switch from one to another. You have to go, often have to go down into the kernel. Because of that, people wind up turning their code inside out and using non-blocking I/O with something like the NIO API. And you can do that, but it makes for much more complicated code. And so many people just don't bother. And servers just wind up being underutilized because, oh, well, let's just do the simple thing, one thread per connection, and you find that on a typical box you can only support a couple thousand connections before it begins to keel over. Whereas if you use non-blocking, you can do tens of thousands. So fibers are meant to address essentially the problem of the cost model of threads. Fibers are a lot like threads, but not exactly. So let's make a fiber here. We'll do it. They're similar to threads, but one of the key differences is, at least in the prototype API right now, you don't. Whoops. you both create a fiber and initiate it at the same time, all in a single method. Right now, there's no way to make a fiber and just have it hang around until you're ready to run it. But this API is in flux, that might change. So here we're going to make a fiber, it's going to print hello, and then it's going to be done. So it prints hello, and then it's done, and we get back this fiber object, and look, it says there in the toString output, no carrier thread. So fibers are essentially user-level threads. Fibers are coordinated and scheduled by the Java runtime system, well above the kernel. They are dynamically mapped onto and off of operating system threads as needed. And the Java runtime system can do that in a very efficient manner. It can also switch between fibers in an extremely small amount of time, measured in nanoseconds rather than milliseconds on typical hardware. So avoiding all those calls down into the OS makes them much faster, makes them much lighter weight. A Java thread usually, a Java thread typically gets an OS thread. An OS thread has a megabyte worth of thread stack and there are a couple kilobytes of data in the Java heap. Threads have hundreds of bytes of data in the heap, and that's it. They only have a thread stack when they're actually running. Fibers are simpler than threads. Here are all the methods, on fibers. And well, at least half of these are like inherited from Java-lang objects, so they're not, but some are not. You can tell if a fiber is alive. You can wait for it to terminate. You can tell whether it's canceled. You can cancel it, and you can do a couple of other things. You can like joining it and so forth. Fibers work well with completable futures from the Java util concurrent API. So if you have code that uses completable futures, you can do that. And they interact fairly well. Let's try that here. If I can remember how to spell it. Schedule. This fiber will just return hello, and there's a convenient toFuture method here. Now we get a completable future. Invoke its get method, we get the result back out. So fibers are, in the present design, one of the obvious questions is, well, do fibers extend threads? Do threads extend fibers? What's the relationship there? In the present design, fibers are in a world unto themselves. So fibers are not a superclass of threads. They're not a subclass of threads. There is a common type that that unifies them called strand that's needed for just a few use cases. But right now they're separate. Yet, the intent is to have a fairly simple migration path from current thread-styled code onto fibers. So I'd like to show you an example of that. So we've got a little web service here. Let me hop into my favorite IDE, namely Emacs. So we've got a little REST demo. We've got this trivial little service. So we're using JAX-RS, import a bunch of the JAX-RS stuff. We're going to find a simple path. And this sleep URL is going to, it's really trivial. It's just going to simulate doing some work. So if you make an HTTP request against the sleep URL, this thing will come in, it'll look at a millisecond parameter. By default, it will sleep for 100 milliseconds, pretending to do some work, and then just return that number as a string. So really trivial, right? So I've got Jetty set up here. And let's run that using threads, as you could do today. Oh, no. There we go. OK, so we run this through Maven, because that's how you build stuff. And then this test is using the Vegeta HTTP load generator to bash on our little Jetty server. It warms up for 5 seconds, then runs for 10 seconds. And we'll get a pretty graph out when we're done. Doom, 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 crank, crank, crank. OK. Let's look at the graph. OK, here is that 10-second run with threads. Now, as you can see here, the behavior here was really spiky. This is not terribly nice. It's very unpredictable. In some cases, it's quite large. Here we've got a pause of about 1.5 seconds. We can zoom in on that. So sometimes it does indeed only take just slightly more than 100 milliseconds, but often because of the overhead of switching amongst threads and everything else and blowing out the caches with all these thread stacks, it takes a lot longer. It's unpredictable. This is not something you would want to deploy in production, and so as a result, you would have a whole bunch of servers, each running with threads, and trying to get this graph so that it's nice and flat. Okay, let's now change this to use fibers. And that actually turns out to be pretty simple. One of the cool things about Jetty is that it's this embedded web server. You don't configure it with like a big pile of XML. You configure it by writing a little bit of Java code, and it's got a nice API for configuring the web server. Amongst other things, you can just tell it what thread pool to use. And fortunately, its thread pool abstraction doesn't actually require that you use threads. It just requires that you're able to do certain basic operations, such as join and get idle threads and so forth, and that you're able to execute a runnable. So we just provide the Jetty web server with a variant of its thread pool abstraction, where we override the execute method and say, well, you want to execute this runnable, throw it on a fiber, let it go. And that's all we had to do. So let's do this test again. With fibers, same attack method, five seconds of warm up, 10 seconds of runtime, hitting this thing at 1,000 requests per second. And let's refresh our graph, and you can barely see it. Whoa, what happened? Let's zoom in on the first second. So the orange line is the response time with fibers, and you can see after initial warm-up period where, up here it was just over 200 milliseconds for one particular data point, it very quickly warmed up, and the response time with fibers was a hair over 100 milliseconds consistently for the rest of this test. That's much better. That's a much nicer graph. And even on this fairly small machine, I could crank this up to like 2,000 or 4,000 requests per second, and it would just work. So that's a pretty big improvement. So fibers are not just for avoiding non-blocking I/O. They open the door to lots of other new techniques, such as channels and data flow and actors. And the cool thing is that all of those techniques will be implementable on top of the Java platform itself. We don't have to build those in. We can have, people can write their own libraries. Maybe a few will become popular for those types of architectures. We don't have to build those all in to the JDK itself. Now, I mentioned continuations. Continuations are the low-level JVM mechanism upon which fibers are built. The Java virtual machine in the prototype actually has no knowledge of fibers. It just knows about continuations, which are essentially a suspendable unit of computation, and then fibers are built on top. A fiber is essentially a continuation plus a scheduler for continuations. But in general, continuations in fibers, if you're familiar with other languages, continuations, for example, have been a big thing in the Lisp community for decades now. It's another example of Java borrowing well-established concepts and techniques from other languages and platforms, and taking them, considering them for Java, and making them look like they fit in, making them be part of the Java platform in an integrated way, rather than just kind of bolted onto the side. Okay, let's move on to Panama. Whoops. Actually, let's not move on to Panama. Let's skip Panama and go straight to Valhalla. Valhalla is about value types and specialized generics. What does that mean? So Valhalla is motivated by hardware, right? today's processors are vastly different from those of 1995. The cost of a cache miss has increased by 200 to 1,000 times. And chasing all of the pointers inherent in Java data structures is really expensive. And there's so many pointers because there's so many objects. And there's so many objects because every object has identity. You can synchronize on any Java object even, which seems cool, but was it really necessary? And this just gets especially painful for big data and machine learning types of applications. The missing abstraction, we think here, is value types. There's no way to declare a pure data aggregator that has no identity, but is still considered to be defined by a Java class. With value types, we'll be able to allocate small objects. I mean, they're not really objects, they're values, in registers. We'll be able to flatten data structures. Or as John Rose likes to say, he has this motto for the project: codes like a class, works like an int. So let's look at an example, whoops, wrong. Matrix multiplication. Yeah, this keyboard is a very awkward angle. All right, real quick now. I'm going to do matrix multiplication here. Main, Java. We've got complex numbers. Public class complex looks a lot like the point thing that I showed before, right? Double real, double imaginary, accessors, an add operation, a multiply operation. And we're going to do a multiply using the usual cubic algorithm. You go across the rows and the columns, you compute the dot product for each corresponding pair, and out pops your resulting matrix. We can do that with, if you just do that today, you're quickly reminded why we don't do matrix multiplication in Java, because it's slow, because every one of those complex numbers is an object, and there's a pointer to it, and there's an array of arrays to make each entire matrix. So here I'm running matrix multiply on a pair of 500 by 500 matrices, and using objects, as you could today, and it's taking almost 4 seconds per multiply operation. This is just in warm-up. I'm using Alexei Shipilev's very fine Java microbenchmark harness, which takes care of a lot of the drudge work of warming things up and measuring things carefully, and so on and so forth. We're seeing in these iterations about 3.6 seconds. Each one is allocating almost 4 gigabytes of memory, and it's taking its sweet time. Let's look at this in a log, so it's easier to see. Okay, here are our results. Each operation took 3.5 seconds when we measure it carefully. About 4 gigabytes, and a very interesting metric here is instructions per cycle. Whoops. So just over 1 instruction per cycle was retired. So the processor in this laptop, it's an Intel Core i7 Skylake, it's capable of retiring 4 instructions per cycle. We are barely keeping it busy. It's spending most of its time waiting for memory. Only 1 ALU operation is completing per processor cycle. Okay, so I'm going to do one tiny thing here. I am going to, let's go back to complex. I'm going to change this into a value class. And I'm going to run that test again. Here we go. Warming up. Even in warm-up, look, it's only taking 260 milliseconds per multiply. That's way less than 3.5 seconds. And we let this go. And we see that that's pretty consistent, 260. It's allocating almost 4 megabytes per matrix multiply operation, and that's just for the result matrix. It's not allocating anything as it's actually doing the computations. Let's go back to our log. I'll leave the Most recent results on the top. Go down to the bottom. Whoops. Okay, we'll just have to remember that. So we're getting 260 milliseconds per operation. We're allocating only about 4 megabytes, and instructions per cycle is a much more respectable 2.9. We're now retiring almost 3 ALU instructions per cycle. We're keeping the processor cores almost as busy as we can. So that's a sample of Valhalla. Valhalla is working fairly well these days. If you want to hear more about Valhalla, again, stay right here in this room. Brian will be here in 10 minutes or less and can tell you more about that. That is a sample of what's going on in the future of Java. Our feature pipeline is richer than it's been in years. This is actually a really exciting time. We've been talking about these projects for a while now, and they're starting to bear fruit. It's really cool, and it shows that Java really is moving forward. Don't believe a word I said? Thank you very much.